Hey guys, so today we are all the way at Bond Enthalpies 6.7, meaning we are really close to being done with this unit. So if you take a look right here, you'll see our learning target. Go ahead and pause here and write this in your own words. So we have four methods of finding the enthalpy, okay, and we already looked at calorimetry when we did unit 6.4, which we did our experiment with that. So we've already done calorimetry. Right now with 6.7, we are going to look at average bond enthalpies. We'll do enthalpies of formation in 6.8, that's going to be our next video. And we will do Hess's law with 6.9. So we are going to do numbers 3 and 4 here in the next couple of lessons. Today's, I think, is pretty easy, so let's see if you think the same thing. So just as a bond energy kind of a review, we know as the atoms in a molecule get farther apart, the potential energy increases. And as they get closer together, they have a lower potential energy. So, and we need to know that that is an average distance between the two. Usually, like for H2, we looked at that that graph a couple days ago, and the bond length is 0.074 nanometers, and that is actually the average bond length for H2. This can change a little bit. It's kind of like a spring. It'll get a little bit closer and a little bit farther apart, but the average is about 0.74. When it gets shorter than that, it is actually going to be a little bit too compressed, and the potential energy will rise due to the repulsion of the like charges. But in general, we're going to have about 0.074 nanometers. That's going to be the ideal potential energy, or the average there. When the potential energy decreases and they get closer together, they're actually going to release energy as heat. That potential energy is going to have to be given up, because this high potential energy here, it's going to be lower here, so it has to go somewhere. So when it's released as heat into the surroundings. So here we go. As you can see this in words now. Energy is always released during the formation of the bond, because that potential energy is decreasing, so it's released as heat as it decreases and is given off. The same amount of energy, this is really important, the same amount of energy is going to be added in order to break the bond that is going to be released in the formation of the bond. So it's going to be the same exact magnitude with just a different charge. So potential energy is always going to increase as the atoms move away from each other, decrease as the atoms move closer together. Okay. So to find the change in enthalpy from bond enthalpies, so it's not the overall enthalpy, but we're looking at the bond enthalpies. You use this little formula here. It's pretty simple. Okay, you subtract the bond enthalpy, the sum of the bond enthalpy of the bonds broken, minus the sum of the bond enthalpy of the bonds formed. Okay, and this is pretty easy to do because these are all going to be given to you in the problem. So here, in order, like if you look at this really easily, 1 to 2, if we're going from here to here, in order to break this bond, let's say you have a certain amount of energy, you have energy of 1, a certain amount of energy has to be absorbed. You have to have plus 1. So in order to break this, it has to be the same magnitude. So you'd have to have a minus 1 in order to break it. So it's going to release energy when you break it. The gain energy when you form it. Okay. So again, to form bonds, it's going to be an exothermic process, because remember that potential energy is decreasing as they get closer together, so energy is released. So it's the bonds broken minus the bonds formed. The products are always going to be at a lower potential energy than the reactants. So bonds broken minus the bonds formed is always going to be exothermic. So as an example, if I wanted to do something like C2H8. If I can write with this pen, it'd be really amazing. So let's try. C2H8. And then we're going to add O2. We know this is just a combustion reaction. So always we're going to have CO2 plus H2O, and we will do some practices in our lesson tomorrow. So what we're going to have to do is we're going to have to break these bonds and break these bonds. And we're going to be forming these bonds here. Okay, so the bonds formed are not going to be the same as the bonds that were broken. So these products here are going to be at a lower potential energy than the reactants were in an exothermic process. I honestly, yeah, this should be exothermic. But that means that this is going to be exothermic because this actually releases more energy than it takes to form these. Hopefully that makes sense. Endothermic, of course, is the opposite. So same concept, but that means that less energy is released in the formation of the products than it takes to break the bonds in the reactants. So we're not going to have a whole lot of energy released in the products forming those bonds. It takes a whole lot of energy to break those bonds in the reactants in any endothermic process. And finally, we're going to do a few examples in class. These are all the examples we'll do, so don't pause there. Just ignore them all. Is that my final screen? I thought I had another one.